Hi everyone, welcome back to my system design series, and these are some of the topics that we are going to explore today. Whether you are preparing for a system design interview or just curious about how large scale application work, this video is for you. So let's get started. First, let's talk about synchronous communication. Imagine you need to ask a question to your friend. You call them on a phone, ask your question, and wait for their reply before hanging up. In computer system, this is similar to using RPC and REST, where one service sends a request and waits for an immediate response. In this diagram, client sends a request to the server and the server replies right away. This method is straightforward and works well when immediate response is required. For example, when you order food online, your application calls the restaurant system to check if the dish is available or not and then shows you the answer immediately. But what happens when there are large volume of requests? Synchronous system become bottleneck because each request is handled one at a time. And if one service slows down, everything else might have to wait. Okay, so what do you mean by bottleneck? Think of it like a narrow section of a pipe. Suppose this is the pipe and this is the narrow section of pipe. No matter how wide the other section of the pipe are, but this section which is narrow, it will restrict the water. In distributed system, if one component is slower or less scalable, it becomes a bottleneck. It will cause the delays and it will reduce the system's overall throughput. For example, in synchronous communication, if the server takes too long to respond, all the other components who are waiting for that response will also get slowed down. This is why the system designers often look at all this bottleneck before designing any system to optimize the system performance. Okay, let's move forward and talk about asynchronous communication. Think of it like sending a text message to your friend. You send your message and do all other activities which you want to do without waiting for an immediate response. If your friend is lazy just like me, you will get the response maybe 2 days after. The text message is handled by the phone network, which makes sure that your friend have received that particular message. Okay. Here, instead of direct call, the sender sends the message to the message broker, which is also called a middleman. The broker holds the message and delivers it when the receiver is available. This means the sender can do all the tasks without waiting for that response. In large system, asynchronous messaging helps to manage high loads and improve reliability. For example, consider an online ordering system just like Amazon during the Diwali festival. Instead of processing each order synchronously, orders are sent to the message queue. Suppose you are ordering some of the products, so this request will be sent to the message queue. So here there would be lot of requests in the pipeline. And then when the receiver is available, this particular request will be sent one by one. So now inside this there would be different topics. Topics is a kind of a pipeline. This is a kind of a whole message queue containing different pipelines, and these are all the messages which are being sent to the receiver. There would be multiple receivers here who will subscribe to these topics and they can receive the message. Even if you are not able to understand this via diagram, we will cover the message queue in different topic, where we will explore message queue and the Kafka system in detail. So let's get back to the asynchronous communication and what are the use case of having the message queue in between. So some of the key benefits are buffering, redelivery and decoupling. So what do you mean by buffering? For example, if the receiver is busy and they are not available for taking that request, this particular all the messages will be there in the queue. This is called the buffering. Now, what do you mean by redelivery? Suppose this particular service crash, then there would be another service which will be taking that particular message, right? So this message queue ensures the redelivery of that message. Now let's talk about decoupling. What do you mean by decoupling is, here message queue don't know who is the receiver. They don't have any access to know the exact details of the receiver. So these are the key benefits of using the message queue in between. In this diagram, you can see that there are multiple producers who are sending the messages to the central message broker, which then distributes these messages to the multiple consumers. As I said previously, that there would be multiple producers who are going to produce a message, and they will pass on this message queue based on the different topics, and then this particular all the messages will be passed on to the different consumers. This setup is similar to kind of emailing, right? For example, there would be multiple senders who are going to send their emails. This will be passed on to the central message queue of the email, and then it would be distributed to all the right departments, even if one of the department is slow. Remember, synchronous communication is like a phone call where you wait for a reply. And how about asynchronous communication? You send a message and then you don't wait for their response immediately. Now, let's explore the actor model. In actor model, imagine each worker as an independent actor working at its own workspace. This actor processes the messages one at a time, which helps them to avoid common problems in multitasking, like overlapping tasks or race conditions. In this simple diagram, actor 1 is sending the message to the actor 2, which will process the message and then it will pass on to the actor 3. Because each actor handles one message at a time, it avoids the confusion that can occur when multiple tasks happens at once. Imagine in an office you got a task of creating an API. Before creating another API, you will make sure that your first API is created to avoid the distractions, which makes sure that you are focused on single task before it is completed. Now let's consider a more advanced example, a distributed actor framework. In this system, actors are running on different computers or nodes, and still they are communicating with each other seamlessly. This is crucial when you are building the large-scale systems like online gaming servers or real-time chat applications. In this diagram, you can see that actors are spread over two different nodes. Despite being on different rooms, they are still able to communicate very easily, as more nodes can be added without affecting the overall communication. Consider a multiplayer game where each player is an actor. The game server handles the movement such as like leg movement, hand movement, or any of the actions from each actors and processes them one by one. This will ensure that the game is running smoothly even if hundreds or thousands of the players are connected together. But one challenge with distributed actor system is dealing with the updates. For example, if you update any part of your system, some actors might be running on the older version of your code. Frameworks like Akka, Erlang OTP, Orlens handle this scenario differently. In the interview, you may be asked that how you are handling rolling upgrades or backward compatibility. Akka might use custom serialization, for example, protocol buffers to manage versions. Orleans might require a new cluster setup, while Erlang needs careful planning for record schema changes. This detail shows that even if you are having the powerful frameworks, system design requires the careful planning. At this point, if you have any questions or doubts, kindly put them in the comment box and I will make a separate video answering all of your questions. Now that as we have covered all the basics, let's see how these pieces fit into system design. Modern systems often use mix of synchronous calls, asynchronous messaging, and distributed actor framework to create robust and scalable architectures. Look at this diagram. A client is using the REST API to get the immediate response while also uses the message broker for the asynchronous processing. And also, meanwhile, an actor system running on multiple nodes handles long-running or complex tasks without overloading any single part of the system. Consider an e-commerce website where a customer's web browser makes the REST call to get the product details. At the same time, when the customer places the order, this particular request is sent to the message broker. While the order processing system implemented using the actors which are at the different nodes, it will pick up the order, processes the payment and updates the inventory system. This mixture ensures that the website remains responsive while processing the orders reliably in the background. In system design interviews, you might be asked how you are going to handle millions of requests per day. And here is how you can explain. For example, you can say that if you want the instant data retrieval, you can go with synchronous communication. If you want to handle high load and ensure the reliability, then you can go for asynchronous communication. And after, to manage the complex workflows and ensure that each part of the system scale independently, you can use the distributed actor models, but also how they come together to build the resilient systems. So for synchronous communication, you are going to use REST or RPC. For asynchronous communication, you are going to use message queues or message brokers. And distributed actor models are used to manage the complex task by isolating the responsibilities and breaking down into the small independent units. Before we wrap up, let's quickly go through some of the questions you might be facing in the system design round. The first question might be why you are using the asynchronous communication over synchronous communication. You can answer them like asynchronous communication decouples the components and improves the fault tolerance and allows the system to handle the load spikes more efficiently. Another question might be why you are using the message broker. You can answer them like it can act as an intermediary queues, buffers and redelivers the message. Another question might be how distributed actor frameworks help in scalability. You can answer them that by isolating the task into independent actors that work at a time. They simplify concurrency and allow you to scale across multiple nodes without complex locking mechanisms. Another question might be what are the challenges you might be facing if you are using this kind of models? You can answer them like that handling version updates and ensuring message ordering or exactly once processing are typical challenges. However, careful design and planning can minimize these issues. Okay, let's do a quick recap. What we have discussed in this video, first we have started with the synchronous call which we resonated with a phone call to a friend. Then we moved towards the asynchronous communication. It is like sending a message without waiting for a response. It's a kind of a text message. Then we explore that how the message brokers behave like a mailbox for buffering and redelivery. Finally, we have explored the distributed actor model which breaks down the task into the small independent workers which are working at the different machines. Thank you so much for watching. I hope this video have helped you to understand these concepts better. And please make sure you like, comment and subscribe to this channel so that it will motivate me to make more such videos. And if you have any doubts or comments, please don't forget to drop down in the comment sections. Thank you so much for watching.